Now these results that we've gotten by ray tracing can also be obtained algebraically. So we're starting with the basic, this diagram where the object is out beyond the radius of curvature, and the image is formed between the radius of curvature and the focus. But I've enlarged them to make them a little bit cleaner. So this is our object, and it has some height. Call that our object height. This is our image. It has some height. It is our image height. Object height. Image height. Okay, and we're going to use some similar triangles to derive what is called the mirror equation, which it turns out will also work for lenses as well, which is rather interesting, I think. But now, if we look at these here, there's a triangle formed here, there's a triangle formed here. If we follow this ray and bounce it off, we can see these two angles are going to be the same just by the law of reflection. And if those two angles are the same, then that means, and we know that these are right angles, and we know that since we know that these angles are the same, we know that these two angles are right angles, and we can also say that these two angles are the same, which means that we have similar triangles here. And similar triangles have sides that are in ratio to one another. So if we say we can take our object height and say that that is proportional to our image height. Since our image height is downward, we say it's negative, so to get rid of that sign, we say negative image height. And we can say that's equal to the ratio of these sides. So from here to the mirror, we call that our object distance. It's how far the object is from the mirror. From here to here, we call that our image distance, how far the image is from the mirror. And those are these other sides of the triangle, so we can say that those two are equal to one another. So that's one relationship that we're going to use to derive our mirror. And to generate another relationship, we're going to look at our C-ray, which runs through here. And we'll go off and hit the mirror somewhere over there. If we look at these two triangles, we know that this angle is the same because those two are vertex angles. And then these are right angles. And so again, we have similar triangles. So from these two, we can say that our object height over minus our image height is equal to the ratio of these two sides. Now, those two sides you have to think a little bit more about. That's still our object distance. That's still our image distance. Okay, but what is this? Well, that's the difference between our radius of curvature and our image distance. Okay. Oh, and that goes with the smaller triangle, so it should go down in our denominator here. Apologies. This right here is the difference between the object distance and the radius of curvature. If we call the distance, the distance to that center of curvature, the radius of curvature. So this is the relationship that we get by drawing these two triangles. So, if we look at these two relationships, then we can say, these both have the object height over negative image height. So we can say that our object distance over image distance is equal to object distance minus r over r minus image distance. And if we fiddle around with some algebra, we can pull off some shenanigans here. We can multiply both of these over here, multiply both sides by image distance over object distance, giving us that 1 equals image distance times this, right? And if we pull out a 1 over, if we pull out an object distance from the top, we get object distance times image distance, 1 minus r over object distance. If we pull an image distance out on the bottom, we get r over, image distance minus 1. So the dO and di cancel out. We're left with 1 equals 1 minus r over dO over r over di minus 1. Alright. And if we continue to rearrange, we've got r over image distance minus 1, just multiplying this over, equals 1 minus r over object distance. And we can add that over and get a 2. We get that 2 equals r times 1 over image distance plus 1 over object distance. And if we remember that for a mirror, our focal length was equal to 1/2 r, we can move this r over. We can say 2 over r equals 1 over di plus 1 over do. And if f is equal to 1/2 r, then 1 over f would be, 2 over r. So then we get our mirror equation. So 1 over the focal length is equal to 1 over image distance plus 1 over object distance. This is the mirror equation. And you don't need to know the derivation. I just did it. And your book did it, so you don't have to. But this is our mirror equation. So if you know the focal length and you know one of these two distances, you can find the other. If you know the two distances, you can find the focal length, and so forth. Knowing any of these two, you can find the other one. It's a handy way to remember this is just, and actually, typically, it's written like this. And the reason that I changed the order there is because a handy way of remembering this is saying, if I do, I die. You can see it's all right there. If I do, I die. That's an easy way to remember what that formula is supposed to be. So that's a pretty simple formula to do calculations with. When you're given, two pieces of it, you can find the third one. There's another one final thing, I guess, related to mirrors, is what's called magnification. And the magnification, as you might expect, is related to how much the image size is different from the object size. All right. So if we the magnification is just the ratio of the image height to object height, and by using this relationship that we got earlier, we can also say that that is equal to minus image distance over object distance, and that gives the magnification. The sign of the magnification tells you the orientation of the image. A minus sign means it's inverted. A positive sign means it's upright. And then the number, if m is greater than 1, that means that the image is enlarged. Or absolute of m is less than 1, that means the image is reduced in size. Okay, and signs are important to keep track of. There's these signs related to magnification, and there are signs related to image distance, object distance. A distance behind the mirror is said to be negative, and an image height is said to be positive If it's above the height is said to be positive if it's above the principal axis, and negative if it's below the principal axis. And I've said all these things as we've gone along, but on page at the bottom of page 919 and the top of page 920, there's a nice little table, or maybe it's not a table. I don't remember what exactly it is, but there's a summary of the sign conventions used with mirrors. So look at that and make sure you keep those. Oh, it's not a. Yeah, it's just a listing of them. But make sure you keep those straight when you're doing calculations.